Good afternoon and welcome everybody to this webinar. It's 3 o'clock. We have a tight schedule and therefore we would like to start in time. Meanwhile, we start, I'm sure there will be a few other people joining us, but that's okay. So I welcome you here from Burgdorf, Switzerland. That's the Bern University of Applied Sciences. We have our photovoltaics laboratory, which you see behind me, our inverter lab. You see the devices on the test, 3 inverters from Huawei, a Sunny Tree Power from SMA, and Fronius Simo. Those inverters are going to be shown today. We will introduce the equipment we have.
Sorry, interrupt you. Christoph, sorry, please continue.
So, and myself, my name is Christoph Bucher. I'm professor at the University of Applied Sciences in Burgdorf. And next to me, we have Theo Zwalen. He will run through the tests today, do the whole operation, and also explain some of the results we have. Before we start with the test, I would like to give you a brief introduction in the whole testing activities we have within IEC 63409 and give you a brief overview over our testing standard. I have already put it on the first slide, but this meeting will be recorded and made available online. So everybody who is here, you should have got the notification and agree to this. Otherwise, you're of course free to leave again. So this standard 63409 series, photovoltaic power generation system connection with the grid, testing of PCE. Our mission with that is a global harmonization of PV grid connection testing standards. We're fully aware there are already many standards. Some are different, some are similar, but there is no global standard to harmonize that. And that's what we actually intend to do with this project. This is an overview. You've already seen that on the flyer. Therefore, I will be very brief with that. You see here in the top line or the top boxes, the grid connection requirements for generation plants. So these documents are being written by IEC TC82, that's System Aspects of Electrical Energy Supply. And these are valid for all sorts of generators.
Ich höre, haben wir da gerade noch ein
Very
Meeting zu.
Testing
Kommen wir
requirements.
schnell runter.
Oh, mit Japanesen, hörst du?
So please mute your mic if you didn't do so yet. You see at the very bottom the testing requirements for different products. In our case, that's photovoltaic products. So within IEC, we have decided to have the testing standards within the technical committees, the product committees, and the requirements. They are subject to the system committee TC8. And in this figure, also this one you have seen on the invitation of the webinar, you have a brief overview over the committees working on that. You have in the top area, again, TC8, which does the whole requirements, also linked to TC57, which is active in the area of communication, for example. And you have at the bottom TC82, which is the photovoltaic committee, which does the testing documents. So that's the very basic setup and organization of our project. I compiled a very few FAQs, frequently asked questions about this document. So first of all, what is it about? It is about testing the grid connection aspects of PV inverters. We call them PCE, so power conversion equipment. It's PV only, and it's only about laboratory testing or factory testing, not commissioning tests or site tests. That's what is out of scope, and that's in the domain of the SC8A, IEC SC8A. Why only PV? Well, that's a very good question. Also, we in TC82 had this discussion many times, and there are a few good reasons for that. The probably most important reasons are that manufacturers and laboratories, they're often specialized to a certain technology. Now you could argue that the fault right-through curve, for example, that would look like the same for all different sorts of generator. That's true, but the way you test it makes quite a difference whether you use rotating masses or wind turbines, 5 megawatt scale, or then PV inverters in the laboratory. And due to these differences, the second point says then we can be more precise and less generalized when we do the testing documents specifically for technologies. So these are the two big reasons. Also, we see from other, like the European projects, that if you combine many different technologies, it's very hard to find compromises. European experts, you know that from the 5549-10, it took many years, not to say decades, to get this document out. And we hope that with a more molecular approach, we do not have to take so many compromises, can do a better document, more precise, focused on this technology. If we look at the other documents, so IEEE 1547.1 or 5549-10, the European document, they have similar scope, but ours is PV only. The others are several different technologies, and ours should be a global harmonized standard. There are already quite a few photovoltaic documents. There is, for example, the 61727 document, characteristics of the utility interface. So here's a list of documents which might interfere and what we plan to do with them. So the first one, 727, that's a very old document. This is going to be withdrawn soon. That was the decision. Then 62116, that's a very well-known anti-islanding document, and that's probably one of the most successful PV documents because it's used wide, far beyond PV only. This is going to be a standalone document for the moment, but we intend to integrate that into our document and to withdraw it one day. The new testing series 63409 is well established. And the two last documents, the 63217, the overvoltage ride-through, and the 62910, the undervoltage ride-through, those documents are intended to be withdrawn when the new testing series is published because they're part of our series as well. Of course, we are fully aware that 63409, the series we are going to demonstrate today, is not going to replace all other testing documents, but it should support the harmonization. And eventually it will also reduce the number of new standards which will pop up from all the different countries and regions if we don't have such a global harmonized standard. To our tests we do here in Burgdorf, first I have to say for your convenience, our demonstration is only partly normative. If we did normative tests, you should get your sleeping bag and wait for about a week or 2 weeks until we have performed only the protection tests. That's what we have discussed in the meeting just a few minutes before. And so therefore, we will shorten the tests quite a lot. On the other hand, full drive-through, it takes a few milliseconds to test. So there we have stretched certain tests that you can actually see that something happens. Therefore, as we are partly normative, we use European values when it's about choosing values. Then also, you have already seen behind me, there are 3 inverters on the test. So for some tests, we will actually demonstrate the tests in all 3 inverters together. That's quite much more interesting to see the results. Of course, again, it's not normative. And we have some combined tests. So we will combine right through first and then protection. That can be normative. So this option will be given in the norm that these tests can be combined. Your inputs are very welcome. Both in the discussion sessions, so I still ask you to mute your mic until we open the discussion sessions. We have twice 10 minutes to discuss during this webinar, and of course you're very welcome to send us emails. Join also the standards writing, send an email either to myself or to Mr. Yoshioka. You have the emails here and also in the invitation. With that, I would like to hand over to my dear colleague Yasutoshi Yoshioka, who is in Magdeburg and will give you an introduction into our testing standard series.
Thank you, Christoph. I'm happy to have such a good opportunity with all of the European people, not only the IEC expert, but also this national committee's expert. Thank you very much for having such a time, and I'm very happy to present our standard. So I'm very busy to accept your attendees now. So checking the attendees list, I will have the presentation. My name is Yasutoshi Yoshioka. Nice to meet you, everybody. I'm Japanese. I work for Fuji Electric in Tokyo, but now I'm in the Magdeburg, Germany, because we use the very elegant test setup in Magdeburg University. So I will explain our testing environment, and in order to confirm some functions of which written in the part 7 and part 6 of our standards, I brought my two prototype inverters from Japan. So I'd like to explain I'd like to show some demonstrations about the testing standards. So now I'd like to start the description about the contents of the IEC 6349 series. So as Christoph said, so we are developing the testing standards in order to confirm the performance of the PV inverters, not the system. And as you can see, the PV inverter has the fundamental function, and then we check the power flow control managed by PCE, power conversion equipment, which is written in the part 3. So then we have the another part, which is the part 4, covering the protection right through requirements. And then today, Christoph will show us some tests according to the part 4. And then part 6, sorry. So covers the grid support functions. Those are very important functions to manage the grid as the distributed energy resources. And then fundamentally, we have the basic EMC requirements in part 5. And then additionally, the part 7 covers a very important function, which created the information exchange between the system operators and then PCE, the provider. So together with the part 6 and part 7, so this PCE becomes a very smart inverter in order to support the grid. Then part 1 covers the general issue, and the part 2 describes the testing requirement, testing environment. So as you can see, they are following the TC8 standard 676. So we will develop the testing standards. And then, as I said, so part 2 covers the testing environment, and it also covers the actual product and scale down product, and then hill and the online simulation, the offline simulation, such like this. And then part 3, as I said, it shows the basic standardized test procedures in order to evaluate the static characteristic of the PQ control. And then, so you can see such a test for the transient characteristic in order to manage the PQ control. So here, there is the list for the EMC issue. So it's a simple two requirements. So you can see at the top. So this part 5 covers the testing requirements in order to measure the harmonics, voltage fluctuation, voltage unbalance, such like that. So referring to our existing IC standard, this part 5 provides the testing conditions and testing procedures. And here bottom, it is very important part. Now we have the
Oh shit, das ist jetzt.
Yoshioka-san, I'm afraid we have lost your voice.
Hello, can you hear me?
Now we can hear you again. Thank you
Okay,
very much.
sorry. So now in the part 5, we cover the immunity requirements referring to the part 41. Part 41 provides the testing sequence or testing procedure in order to confirm the performance of the frequency measurement. And then there are several new items to be listed here, like frequency modulation. Sorry. And then such like a harmonics, oh, sorry. Wait a second. So phase step change and voltage dips. It's similar with the existing IC standard, but we mainly confirm the frequency measurement performance following the part 41. But unfortunately, part 41 gives the simple test in order to confirm the frequency measurement device. That's why we need to adjust such a testing method for the inverter. This is a very important point for us. And now here, we would have the demonstration from the Burgdorf, and mainly the Christoph will cover the part 4 requirements. And according to part 4, we listed such requirements: voltage protection right and right through, and the frequency protection right through, and the voltage phase jump right through. So, but there are several existing standards, as Christoph said. So we need to refer to 6025 series and also the UVRT standards provided by TC82. So then in this, for this part 4, we have already made some experiments in Burgdorf supported by Christoph, Professor Bucher. So we, in January this year, 2023. So we went to the Switzerland in Burgdorf. We had the 2-day meetings with him. And at that time, on the second day, we demonstrate some tests following the part 4. So here, as you can see, in the Burgdorf, I brought my prototype inverter, and we connected this inverter to the power system testing system. And then also we have discussion with Christoph and his staff. So, and then here we implemented such test about the over frequency and the frequency, and then we implemented some test in order to evaluate the over voltage right through equipped with my prototype inverter. So also, as I said, so which was the online demonstration, and then we had several discussions with the TC82 members through the online. So I'm very happy to have such opportunity in Magdeburg, in Burgdorf, in January 24. Sorry, is it 3? Then today, so Christoph will provide the additional test following the part 4. Then I'm happy to introduce his laboratory now. So Christoph, please take your display. I'm finished. Hello, Christoph, can you hear me?
Thank you very much. Sure. Thank you very much.
I stopped my
Your
sharing.
done?
Yes.
Welcome back to Burgdorf in our photovoltaic inverter laboratory. Before we show you the tests, I will quickly go through our lab and show you what we have and what we want to test. I start on this side, so you can see our AC grid emulator. That's a 3-phase linear grid emulator, linear, so we can also do EMC tests if we want, and we have as little distortions on the frequency as possible. Next to the emulator, we have, I just hear from the central regie that we don't have a picture. Let's make sure you can see us. Here we go. Thank you. So I start again. We have on this side our AC grid emulator, 3-phase linear. Next to it, we have our multi-string PV simulators. We can emulate IV curves with this, so they are linear to have as little influence on the inverters as possible. Then we have our devices on the test. It's 3 inverters, Fronius, SMA, and Huawei. Those we are going to test today. And to evaluate the tests, we have here in the middle first an oscilloscope. We don't necessarily need that for the normative tests, but we use it to have a better view what actually happens. And we also use it for a special test today. And we have here our power analyzer, Yokogawa high precision measurement tool to measure the behavior, but also the frequency, the voltage we have in our inverters. And then behind this wall, we have our special guest today. That's especially for our Swiss guests. We have an external interface protection system, an interface protection system that's integrated in all inverters. In several countries, it's still mandatory to have that as an external product to your inverter. That consists of an interface protection relay, which senses voltage and frequency. And it also consists of this interface protection power switch. So a power switch which will disconnect the inverters from the grid if frequency or power is, frequency or voltage is completely out of range. Today, we are going to do 3 different tests. So the 3 tests we are going to do, they start with tests where we do not need this external switch. Therefore, I hide it again behind this wall. We start with 2 standard tests. The 2 standard tests, the first one is under voltage right through and under voltage protection. This we will perform that as a combined test, and we perform that on 1 inverter only. However, we'll then show you in the results how the 3 inverters also have behaved, so that you see that they all behave basically correctly, but they don't behave exactly the same. In the second test, we are going to do a frequency watt test. So we show you how first the power control function reacts on a change of frequency, and if the frequency changes too much, how the inverter protection will then disconnect the inverter. So these 2 first tests, they are normative tests, more normative tests, and the third test then, that will not be a normative test. That's the test to show the difference between the behavior if an internal disconnection switch or protection switch acts on the inverter, or if we use this external interface protection switch. Now I would like to hand over to Theo. Theo will guide you through the different tests, operate the demonstration, and explain the results.
Okay, welcome from my side. As you can see on the presentation, I have here the wiring diagram, how now everything is prepared. You can see on the left side the DC source, which gives the power to the inverter on the test, then the inverter itself. In blue, you can see our measurement equipment, and then on the right side, our AC grid simulator. On this slide, you can see what should happen in this test. This black line is the voltage, how it's written in the standards. We do just go down with the voltage quite a lot to 30% for just a short time, and then go back to the nominal voltage. And while the inverter shouldn't disconnect from the grid. He should stay on with injecting power to the grid. On this slide, you can see the measurements we did in an earlier test, in this time with 3 inverters instead of 1, how this under voltage right through looks like. In blue, we can see the voltage, and in orange, the power which was injected to the grid. Okay, let's start the test now. I'm just starting everything. It needs some time to recalibrate all the measurements. What you can see now is the voltage and the power just in some seconds. It doesn't really show what we should see now. Sometimes our online view is quite difficult. Yeah, unluckily we can see, but the test is already happening. Yeah, sorry for that. What we can see here on the oscilloscope, we had the disconnection in the end. I will show later what exactly happened. Necessary up to now is here we can see in blue the voltage and in orange the current, which was disconnected when the voltage went too low. And on the other hand, in the voltage, we can't see any change while the inverter was disconnected.
Now it's back on the screen as well.
Yes, now we can see what happened in the test. Yes. So let's change back to the presentation. I explain now what happened in the orange line. That is the power that was injecting to the grid. While the voltage went down, the power was really fast back injecting to the grid. That's how the inverter should handle such a voltage fault. Then go to the next slide. This is quite difficult to get in the live display. That's why we have it in presentation. It's the same situation. The blue line, which represents the voltage, went down to 30%, and the inverter then tries to increase the current such that he can bring the power into the grid. That's quite difficult at that low voltage. But as you can see, when the voltage came up again, it had really fast again, the current should have to inject the power to the grid. Okay, and then in the end we had the under voltage disconnection. That is what you can see now is from an earlier measurement, this situation. First, the voltage went down just in the area before the inverter's disconnect. And then it ramps down until all the inverters disconnect. And the step you can see in the three orange lines, this is when the three inverters disconnected and the power they inject to the grid went to zero. And as you can see, they weren't really at the same time. They had just a space between, but all of them were in the standards. They passed the test and were in the tolerance. Okay, that was already everything from the first test. And we go now over to the second test. Donna, can you please give me first the presentation? Just a moment, sorry. Yes, here we are. And then next slide. Again, next slide. That is what we have seen in live. So the next test is the power reduction when at the over frequency, and then in the end, an over frequency protection disconnection. The setting is quite similar as before, just one inverter connected to the grid, and the rest is all the same as before. Next slide. And that's how it looks like in an earlier measurement. In blue, we have this time the frequency, just jumping first to 51.4 Hertz, and then ramp slowly up until the inverter's disconnected. Okay, let's do now this test in live. Okay, I start now the test. What we can see now on the left side is how the inverter tracks the power point. When he can bring all possible power to the grid, he try always to be on top in the blue power curve from the panel. And now, just some seconds. Now we can see the view on the right side. And on the left side, we can already see how the inverter reduces its power because of the overfrequency. The frequency we can see on the right side in the under part of the figure. And now on the left side, the blue lines totally disappeared. That means that no power is injected to the grid anymore. So the inverter disconnected because of the under overfrequency. So we go back then to the presentation. And at this point, I pass over to Christoph because I have to change some things in wiring and he can explain what happens with the power.
Okay, let's again have a look at the measurements we have got here. I'm fully aware you don't really have the possibility to fully understand what we all did because it goes so quickly, but we think 1.5 hour webinar is enough. So we try to really condense the content and you'll also have the chance to watch it again offline later on. So if you look at the graph here, I try to explain this graph, what should have happened, what has happened. Hopefully it's, or now I can say it's more or less the same. So these inverters have passed the test. When we start this frequency watt control and our frequency protection, so what actually happens or what we emulate is we assume that the frequency first is at 50 Hertz. That's what you can see on the very left of this graph. And then there's a frequency jump from 50 Hertz to about 51.4 Hertz. With this jump is big enough that the inverters should all ramp down their power, but it's small enough that the inverters should still stay connected to the grid. And that's what you can see with the red lines. The red lines are different lines, and they are marked with P as a function of F. That's actually the active power from the inverters, which is reduced from 100% down to about, what's that, 50, 60%. And you can see how all three inverters, that's the measurements of all three inverters together, they all have reacted correctly. They all went to the same power level, but you see that the speed, how they reacted, when exactly they reacted, that differs a bit. And it's the challenge now in our testing code to evaluate this behavior and to say what is good enough, what is not good enough, because of course the standard itself, the grid code, that wouldn't tell us how exactly it should behave. It would just tell us where and about in what speed this behavior should be shown. We see then in about the middle of the graph, so that's after roughly 10 seconds, if you look at the time axis, that the frequency has been ramped up. So frequency goes up even more, and with the ramp up of the frequency, you see how the power is being reduced more, only a little bit. And then we come to this protection area at 51.5 Hertz about, and then you see how all the inverters disconnect. You see two of the inverters, they connect exactly at the same time, whereas the third inverter, that disconnected only a bit later. That's both okay, both within the range. Also here, the testing specifications must define pass-fail criteria and say what of this behavior is still okay and what isn't. So these are the results which we have pre-recorded. You have seen before our live demonstration. For understandable reasons, I guess, we have separated the live demonstration and actually the discussion of the results, because like this, we could already mark some or indicate some things which are easier to explain once they are recorded and slightly treated. Now, the next test is a test which is going to be completely different from everything we have done so far. Because now we leave this normative testing and we go over to the question of the interface protection. Interface protection in German, that's NA-Schutz, and I've seen there are quite a few colleagues from Switzerland online now. We have this project called NAEEA+, which is a project from the ETH in Zurich, where we try to investigate whether or not the external interface protection has enough benefits that we actually can support the grid with it, or if there are too many drawbacks, costs, additional risks, if we do not have that. Now, it's not our job to judge whether one or the other is the case, but it's our job to demonstrate what actually happens if we have an external interface protection switch. Now, just showing that the switch opens when it should open, that's a rather trivial question. So what we actually do here, that is, we will show you, first of all, our 3 inverters. And now we will not connect these inverters to the grid directly, but we will connect them to an interface protection switch first. What we also do, as we are not in a standardized test at the moment, we take this cable, you can see the cable here on the floor, and we connect the inverters through this cable. You can also see here some more cables on the floor. It's about 50 meters. We don't have these cables here lying around because we were too lazy to clean up our laboratory. Well, maybe yes as well. But there's another purpose for that, and that we want to have some real grid connection to study the effect. What happens if we open a switch while 3 inverters are running full power behind it? And to study this phenomena, what we will actually do is we operate the inverters at certain power. We manipulate the frequency, and we have set the settings of the interface protection switch in such a way that they will disconnect first. We have already studied before what happens if the inverters disconnect, but now we'll study what happens if the external interface protection switch disconnects first. But at this stage, I would like to hand over to Theo, who can explain you slightly better what is going to happen, and we will look at the results, how it happens.
Thank you. Yes, here again we have the wiring diagram. While Christoph was talking, I have prepared the new wiring, and as he already said, we have now all 3 inverters connected together, and then in the middle of this figure we can see this external interface protection, or this NA-Schutz. And then we have again the measurement on both sides and our AC grid simulator. And what we will do now is we do as we did before, under frequency, this time under frequency and lower frequency protection test. So we jump down to around 47.6 Hertz, and then a little later we begin to ramp down until not the inverters but the external interface protection disconnect the whole system from the grid. Okay, I will start now this test. Hope everything will work with our view. Now the measurement should be ready, but we can't see anything, unluckily, again. Anyway, it will, okay. Unluckily, we couldn't see on the live view from the measurement equipment, but what we can see and what is even more necessary is the view of the oscilloscope. We can see that just before here, the voltage was at nominal values, and in orange the current was injecting power to the grid, And then around here was the disconnection. As you can see, I hope you can see, perhaps I can zoom a bit in. Like that. At one point, the current don't follow anymore at a Zenos signal. That is where the external interface protection disconnect the system. And then the voltage can't follow anymore the Zenos of the grid, but he tries to give out his voltage as he should. And that leads to that the voltage increases to quite high values. That's just because the inverters can't following the grid anymore. Anyway, the external relay does disconnect the system as it should, everything's fine, but behind we have this high voltages. Okay, that's what we can see in this test.
Thank you very much.
Pass again over to Christoph. Thank you everyone for watching.
So that was basically it, the test we wanted to show you. Now, the next 10 minutes, we would like to open for questions. You have seen, we're very glad to have more than 100 participants, 112 participants, I can see. Yeah, I have to admit that we didn't administrate the webinar for so many people. So I have to ask you to keep some discipline and switch off your mic if you're not talking, or if you should not be talking. And for the next 10 minutes, we would like to open the discussion. You are very welcome to ask questions, give your remarks to what we've had, what we've just seen. I kindly ask you to raise your hand so we can call out your names, state your name and affiliation, and ask your question. And Yoshioka-san and myself will do our best to answer these questions.
My pleasure.
I also look to the chat.
Now, can you hear my voice?
We can hear you.
No, thank you.
Yes. Are there any questions from the audience?
I haven't seen any hands. Yeah, I have a comment. I have a comment about this phenomena. Okay. In Japan, it was 10 years ago, we had a similar phenomena. Or when the inverter detects such a deconnection from the grid, so inverter shall manage such a over voltage behavior in the system itself. So then, controlling the current internally, so inverter can avoid such a behavior. It was required. So I received the question on the chat. So first question, are those all grid forming inverters? Simply no. It is the general inverters, which are called as the grid following inverters. It seems to be the current source inverter. Okay.
Yeah, and the second question, I think I can answer that. At what power level can we test? So the system you have seen now, here we only test up to, with this linear inverter, we only test up to 15 kilowatts. But we will receive actually still either tomorrow or the beginning of next week a grid emulator of 150 kilowatts. So we will be able to test up to 150 kilowatts in near future. Inverters, by the way, to add to Yoshioka-san's explanation, these are off-the-shelf inverters. And actually the whole tests we do here and also the questions with the interface protection, the question is about nowadays inverters connected to the grid. But the question is, are we on track or not with today's regime, how to connect them, how to test them. And we are fully aware if you go to grid forming inverters, there will be a whole set of new questions raising up to that, because the grid forming inverters, when they are operated in islanded mode, for example, of course, they should not disconnect. They should stay connected to the grid or stay connected in production mode, even if the grid is gone. And there we have to, depending on the settings, and there definitely we will need new testing requirements, new testing regimes, and also new requirements on how to deal with them in the grid.
The next question about the voltage life, and also the inverter has the over voltage detection and protection, because when we have the light role in the grid, so at that time at the terminal of a PCE, so a PCE detect the inverter detect the voltage rise. So that's why the PCE faced such a over voltage phenomena. PCE shall disconnect, and then over voltage rise through as well as the equipped with this inverter. No, conventional inverter doesn't have, but the future inverter will have. So Gunnar, raise your hand. Gunnar.
Yeah, thank you very much, Gunnar Kester from Germany. So when we see this test set up as a kind of house with a PV number 1, with a PV number 2, and the third inverter, let's say it's a battery inverter, and I want just to go islanding and open the main switch of the house. Do we have this over voltage equipment, this over voltage problem as well, or is the microgrid ready equipment which is intended to run in the island? That means there must be a central switch to be opened so that the remaining part of my house goes into island mode, runs on its own. Is this only a problem here with the interactions of these 3 inverters, or is it a general problem with the over voltage?
Yeah, I think that's a very good question. I try to answer it. Maybe Yoshioka-san, you can add on to this. So the reason why we have this over voltage here, that's basically because the inverter is a current source here. The inverter doesn't really care what voltage we have, but it injects here a given power to the grid depending on its source. Now, when you disconnect from the grid and you have a very high impedance, so the inverter is just hanging in the open air, we have still a current source which tries to form a current on top of a grid which is not there anymore. And that's, of course, a control mode where the voltage is hard to control. Now, what you mention, or what you ask, if I understand you correctly, if this was an intended operation, so if we have inverters which are intended to form a microgrid afterwards, they would not have a current source, or at least not mainly a current source, but they would also have a voltage source mode. And that's something we see with hybrid inverters already today. So when they are disconnected, they switch over to voltage source, and in the voltage source, they will be able to control the voltage even if there is no grid connected to it. So I would say, yes, this is a typical phenomena for non-grid forming inverters, which are connected to the grid. And then still an add-on to the question before, well, if the internal disconnection switch opens, so if we do the same experiment, we go down with a frequency and we disconnect, and the disconnection switch is within the inverter, then this over voltage, of course, is not visible to us because it's inside the inverter, so contained inside the device. And both the switch and the device, they act in parallel as one device. What we have seen are certain peaks on the AC cable, so the cable which I'm standing on, or which is underneath myself. On this cable, which is the grid cable, there we have also measured some voltage peaks, but they are very, very tiny. And of course, it highly depends on the amount of current which is flowing, on the length of the cable, on the characteristics of the grid. When you disconnect a high power, whether there's a voltage peak or not. But again, if we open it at one central point and disconnect a big power at once, the power peaks on the cable are of course higher, as if we have the inverters which disconnect more or less at the same time, but not synchronized.
Yeah, then next question. I do not have any information from me to be added. Okay, then next question. Hello?
If there are no more questions, I think we are well in time. But
No.
then
So there are one question remaining. So how do the demonstrated test? So it showed the contradiction with the RFG, or then maybe this test provided by you is not does not follow the RFG because you use the 3 parallel inverters, and then it doesn't say anything about such a condition. I think it's an extra test using the parallel inverters. Yes, next, the Hefner. So you had a question. Oh, you, sorry.
Yeah, thank you. I have a question regarding to the fault rise-through measurement. When the voltage fault appears, there was a big transient current peak at this time, and I would like to know: have you measured the maximum amplitude of this peak, and do you know what is this amplitude in percentage related to the rated power of this photovoltaic converter?
we have not measured it directly, but we're trying to get it. Can we have it back on the screen? Have a look at it. Maybe Theo, you can comment on it.
Yes, exactly.
First of all, we have to say that, of course, depending on the exact phase when we disconnect, the results are always slightly different. That's also the reason why we have pre-recorded that, because it's more or less hazardous what behavior we see in actual tests. But maybe, Theo, you can add on to this.
Yeah, I cannot tell a lot. I didn't really have a quite look at this transients. What I can say is it looks quite different at another inverter. It's just totally different at each inverter. Some inverters go for this short time where the voltage is really low. They just go to 0 for a short time. This one tries to increase his power, or his current to stay on the power level. But I didn't really check how they look in a close view.
It's a general. Excuse me. It's a general behavior, as Theo said. Now that you can see the low level of voltage, but from the DC side, the power supply gives the constant active power. So in order to keep such active power, the PC shall raise the current to keep the input active power. So match by the current with the voltage low level, so current level goes up. This is a very basic phenomena of the current source inverter.
Yes, I understand. My question was regarding to the transient peak.
Sorry.
So what was the maximum current transient peak at the time when the fault appears?
It is actually the current control, and then when we see such a disconnection of the conductor, so just it's a behavior of your capacitance in front of the PCE, and you can see such a transient, but it doesn't cause any problem to the PCE on the split and a very low level. So the PC can manage the level, then maybe the 120% or 130%, the PC shows such a spike level. I think this is a good answer for you, I hope.
So thank you very much again. We are 20 seconds ahead of time. I would like to use this momentum, hand back over to Magdeburg, and Yoshioka-san, please go ahead with the next part. Thank you.
Yeah, thank you very much. Wait a second. So now from our side. So now we have another display showing our slide. So here, I would like to explain our side. Then today I would like to demonstrate the remote control equipped within their PCE. So as you can see here, now that the grid support functions are programmed in this PCE as the additional function, then externally we have the management system using the information exchange function. So today I would like to demonstrate those functions. So before going into the demonstration, I would like to explain what the power control and the grid supports are. So in part 6, we cover the testing procedures in order to confirm the performance of the connect, disconnect, and the constant power control and response control against the grid variation. So connect, disconnect is very simple. From the grid, so PCE can disconnect intentionally or connect intentionally if there is a request or a command. And also here you have the constant power control. So you can change the feeding power or feeding active power or adding the reactive power as you want from PCE. But we have to consider the input current from the DC side. Like a PV inverters, we cannot manage the level of the input current. And then at that time, we need a storage. At that time, we can control the active power. So then in terms of the active power control, like a STATCOM, so PV inverters can control the reactive power control as it wants. So then according to the response control against the grid variation, so we can see the fluctuation of frequency and voltage. Then following such a deviation, the fluctuation, PV inverters can control their active power and the reactive power. So as you know, when we manage the frequency variations, so PV inverters can control the injection of the active power. So and then like a STATCOM, if the PCE or PV inverters detect the voltage fluctuation at the terminal, so in order to reduce such a deviation, so PCE can manage the reactive power control. It is a very simple autonomous control. Then with the remote control, those functions can be remotely controlled. So now here we have the remote control, as I said, and then disconnect and connect can be managed by the energy management system from the system operator or the aggregators. And then such a constant power factor and also active power level can be managed by the energy management system, as you have now in Germany, also the Switzerland, and also in Europe, all of your national countries. And also in Japan, we have the reduction of the active power control following the request from the system operators. And also here you can see the remote configuration to change the parameters of grid support function. Now inside the PCE, for example, PCE has the voltage bar control. So you can manage the slope of that voltage bar control card. And then also frequency watt as well. Then also you can change some level of the protection, like over voltage and under voltage, over frequency and frequency. And also, so we can manage the several time point or the voltage point for the UVRT and the OVRT. And the frequency right through also local. So remotely, we can manage everything through the such an information exchange. So now under TC57 of IEC technical committees, so their information exchange behavior is modeled according to the IEC 61850. So such like WAD, intelligent electrical device, and the DARMs are defined in 61850. So now today we will demonstrate our such a remote system based on the such a 61850 protocol. Then here part 7 covers the minimum required parameters for information exchange. because the 61850 provide the several parameters as the information model. So sites like a name of the vendor and so a serial number can be monitored from the energy management system. And then such like a status of the voltage protection and frequency protection, those can be monitored by using the such information model specified in the 61850, -7-4 and -7-420. Now, today we will demonstrate the constant power control and then remote configuration. So here is one of the example. So in the PCE, we have already programmed such a information model as the parameters. So active power control can be managed with those parameters. Also, internally, the voltage power control can be deconfigured by changing those parameters. For example, so we have the characteristic curve for the voltage bar. Then remotely, we can change such parameters showing the characteristic of the curves. So also we can manage the response time and ramp time for the voltage bar control function. So this is a very important point to be managed such a remote control function. Today, we will demonstrate the volt-watt function. Volt-watt function means that when PCE detect the voltage rise on the grid, so in order to manage the such a voltage deviations, so PCE reduce the power. So it is their mandatory requirements in Europe now. So in a low-level voltage system, such as a distribution system, it is dominated with the resistance component in the grid. And then when PV inverters produce their power, active power, so we can see such a voltage rise at the terminal of the PCE. Then, so PCE try to reduce the power from the DC side. So this is the mandatory in Europe now. So today we will show some behavior of the such a voltage watt function, but not today. We will see the special test by using the 2 PCE. So here we have the 2 PCE, and then if we have the unbalance of the impedance to be connected to the PCE, we can see the different behavior of the feeding reactive power. So for this case, so PCE has the same voltage watt function characteristic like this. But in order to, due to the such additional line impedance, so PCE reduced the power to this point, and then it caused the inequality or the imbalance of the feeding power to the grid. But now that remotely we can change the such a volt-watt function curves like this. So if we change the PCE1 curves like this, so we can keep the feeding power from both sides equally. And also, we can manage the reactive power from the PV inverters. And then now the PCE produce the reactive power in order to keep the voltage. So PCE1 can increase the power by managing the reactive power control. So now today, we will demonstrate those functions. Then we can control such functions remotely from DOMs like this here. Here, we are in Magdeburg now. So in the Magdeburg University, there are many power supplies and then with simulators and the roads, and then we brought our 2 inverters. So we created such a test environment in this laboratory. So as you can see here, so I brought the PCE1, PCE2 from Japan, and then we connected the IED to the PCE here. And then we have the laptop computer in order to apply the DAMS function from the this PC, this laptop. So this is the environment of this test laboratory. So now I would like to show the my inverters physically. So here. So now this is the PC1, and this is the PC2, and this those PC has the interface for the information exchange. We call IED. The IED1 is here, IED2 here, and then this those IED are connected to the DAMs next to the table. So, but I cannot show you. But this IED is connected to the DAMs. So then now here we have the additional component here, such a glass. Inside the glass, we install the additional impedance having the resistance and the inductance. So it created the unbalance of the impedance, then PCE1 shall reduce the power when the PC1 provide the active power. So now I would like to ask Mr. Hofner to explain the testing environment, such as the DC power and AC power. So please start.
Yes, thank you, Mr. Yoshiyuka. First, I would like to welcome you in the Power Quality Lab here in Magdeburg. And as you can see here, we have here 5 cabinets, big cabinets, where the first 4 of these cabinets are our AC power supply, and the 5th cabinet is our DC power supply, or a photovoltaic simulator, especially. And from the AC power supply, we can see here the first 3 cabinets. This means this is the amplifier for phase 1, phase 2, and phase 3. And the 4th cabinet is our control unit and the grid impedance unit, which controls the amplifiers. And each amplifier has a power of 15 kilowatts. So in sum, we have 54 kilowatts here in what we can simulate or create. And we have a surface for these AC power supply where we can manipulate the waveforms in such a way that we can give them harmonics, that we can say we have unbalances, we can do voltage steps, frequency changes, and so on. And what we create today is we make some voltage steps, so amplitude steps for in sequences. And yes, we look to the behavior of Mr. Yoshiyuka's PCEs. And here the photovoltaic simulator has a power of 25 kilowatts in sum, and we can manipulate this in such a way that we can have photovoltaic curves, maybe as you can see here. Yes, now, yeah, we can follow such a curves of photovoltaics, and yes, but we will not do this today. We will just use the PV simulator as a DC power supply with a voltage of 500 volts and current limits. So maybe finally just briefly information about the measurement devices. We use power quality transient, power quality recorder, where we can measure from transients too, but mainly the power quality phenomena. And in addition, we have an oscilloscope just to have a closer view to the waveforms. Yeah, and I think I should give to you back.
Thank you for excellent presentation of this laboratory. So now I would like to describe here about our demonstration. So now you can see my slide. So here we have the 2 PCE like this. And then as you can see, if we have the balanced impedance on the line, so PCE can manage the balanced feeding power from the PCE. but the if the inverter has the additional line impedance in front of the PCE like this, so we can see the unbalance of the feeding power, active power from PCE. So today, I would like to demonstrate it with such figures. So then using the DOMs, we will show the such unbalanced behavior of the PCE, two PCEs. Okay, let's start the grid emulator. Okay, so we need a time for 2 seconds or a few seconds. Wait a second. So wait a second. Then now, so as I said, from the DOMs, we can monitor the behavior or your such a deviation of the voltage and active power. So now you can see the graph on the display, and at the top of figure, so you can see the terminal voltage of PCE. So now you can see the such change of the voltage step by step, and at the bottom you can see the power injection from PCE. It is the actual active power with both inverter. So red line, blue line shows the active power from PC1, and then red line shows the active power from PC2. And then you can see the other two lines at the middle. So it shows the reactive power from the PCE. Now that they're at the top, you can see the voltage rise step by step. So then PCE 1 and 2 detect such a voltage rise, and then following the voltage watt function, so PCE 1 and 2 reduce the power. But as you can see now that the PCE 1 with the blue line shows the further reduction comparing with the PCE 2. So this is the actual problem. Then so when the voltage goes down, then PCE 1 and 2 reduce the power. Almost there are no power in the grid, so they don't detect the difference. So now the voltage goes up, then the PCE 1 and 2 recover to produce the active power. That's why the PC1 can detect the further high voltage at the terminal PC1. So PC1 shall keep the lower level of the active power comparing with the PCE2. This is the actual behavior in the field. We can expect that behavior because in the grid, we will see such an imbalance of the impedance in the grid. Then now, so we will change the characteristic curve of the voltage watt function. So in order to keep the balanced feeding power to the grid, so now remotely from the DOMs, so we will change the characteristic curve like that, the green curve here. So we can keep the voltage balance of feeding power. So now from the DOMs, as you can see, so we can manage the parameters of the PCE1 like that. So remotely from the computer, so you can change the characteristic curves like that. Then, so you can see the remote control or remote configuration functions with this figures, monitor card. So now we changed the parameters of a curve like that. That's why at the bottom you can see the red line and blue line shows the same level. So now we changed the parameters of a voltage watt function inside the PC1. Then PC1 change the point of the control of the feeding power. So the PC1 and the PC2 can manage such a balance control. Also from the DOMs, we can monitor those their behavior, and then so we can manage the such a parameters remotely. So now we change the parameters of voltage watt functions with the previous parameters. So you can see the unbalance again. Then next, so using the reactive power control, so we can manage such an unbalanced condition at the PC1 terminal. So by injecting the reactive power from PC1, so PC1 can manage the voltage rise at the PC1 terminal. So then when the PC1 inject the reactive power, so you can see the such a balanced active power from PC1 and PC2. Okay, then we will try to change the parameters of the reactive power control from DOMs. We will show there's such a remote control display here. So now this display shows the remote control display, and then you can manage the reactive power remotely from DOMs. Please set the reactive power level. Yeah, now the remotely the DOMs set the reactive power adequately. Then you can see the red line, the blue line shows the same level by changing the reactive power from PC1. So PC1 injected the reactive power. So at the bottom of here, and you can see the midpoint. So with the it's a green curve. So green curve shows the reactive power provided by PC1, and then so now that the PCE1, sorry, at the top of the figure, you can see the difference of the voltage level at the PC1 and PC2 terminals. So because now that the PC1 shows the such a compensation of the voltage rise, that's why the PC1 can manage the equal voltage power feeding to the grid. Okay, this is our demonstration from Magdeburg. So thank you very much by showing such a demonstration from Magdeburg. And then now we finished this demonstration. Then today I show the such a remote functions and remote configuration as an example by using the both watt function. But inside the PCE, we have the furthermore control functions like the voltage bar control and frequency watt control. We can manage everything from the DOMs. So if we have a time, I'd like to demonstrate all of things, and then we can so discuss this such a controversial point. But now that it is a very important point in order to consider the such a coordination of the multiple functions. Also, the our standard testing standards, we have only the single PCE to be tested. But in the future, we have to manage such a multiple PCE in the field. Also, the such a multiple communications from the energy management system. But unfortunately, now that the IEC standards do not cover this point. Thank you very much for your for this presentation. If you have a question, so I try to do my best in order to answer your question. Thank you. Okay, then, are there any questions? So, Gunnar, page 23.
Yeah, so that was when you go back to page 23 of your presentation.
Yes. So maybe there are
Exactly this one.
yeah. Then
I was just asking myself what means fair and unfair. Why unfair?
Sorry,
Because
we don't know the acceptable sufficient word to show this problem. So we use such a fairness and unfairness, but it seems to be the just unbalance of the feeding the active power from the PCE1 as the PCE provider expected. So I mean that here, so at the top, when we implement the such a both function, so PCU1 and PCU2 operate equally. But in order to, due to the such a unbalanced line impedance in the grid, we cannot, PCU1 and PCU2 cannot manage the balanced feeding power. Then we use such a fairness and unfairness in order to describe the such a market service.
Yeah, I see it that of course there's a difference when your point of connection is next to the distribution transformer or further far away. But what you could do is to make a fair treatment to all the users, grid users along this low voltage line is just to use adaptive control, which assesses the usual fluctuations of the voltage. And of course, at the beginning of the line, they look differently than at the end of the line. And therefore, just use a kind of histogram which measures what has been seen in the past with the voltage. And then you would just use an adaptive controller. That's at least what I would do if I was the regulator who proposed some kinds of curves. So to make an adaptive control, not with fixed values, but saying, well, this is a higher percentile of voltage measurements of the last 3 days or so. So it's also a different situation, of course, in summer than in winter when there's not much PV. But that would be my recommendation. Thank you.
Yeah, it is actually our interesting point. So now we have such functions, remote functions. As I said here, in the standard, we have such information exchange requirements, which are which is managed by the system operators. So we have such a remote function. So then this is a simple question from us. Do you want to use such a function intentionally in order to manage the such unbalance of the power feeding, or you don't need? So then if the market needs such a remote control in order to control the activity to the PCE or the PV inverters or storage, so you can utilize such a remote function and remote configuration. This is just a suggestion. Then I don't mean that we need to specify that the unbalance compensation in our standard, but in the future we will see such a program from the producer point of view. So then, where is the question? Sorry, PUE is more effective. Yeah. Yeah, that now that we see such a function with the constant DC power supply, that's why it seems to be the storage inverter. That's why now that from the DAMs, we can manage such remote control. So PV inverters, in the case of the PV inverters, so we need to consider how we utilize such function according to the DC side input. So next, what the typical overall response time of an inverter to power plant controller PPC. So it means that how much time is required. Depending on the connection of the information exchange devices, I will share my screen now. So as you can see here, now we use the 2PC And then from DAMs, we see the only 2 IEDs. But in the case of the field, so I had that the 1000 IED and the PCE are connected to the one energy management system. Maybe we will see the some conflicts for the information exchange. And so I'm not sure the actual response time, but now that we designed such a system with the 1 second monitoring time. So I'm sorry, I don't have the exact answer to you. So it depends on the design issue, the 1 millisecond or the 10 millisecond, 1 minute, every 1 second. It depends on the design of the such a control or your information exchange system. So are there any questions for the including the demonstration from Christoph from Burgdorf? You can raise your hand. Are there any questions? So, Christoph.
Yes.
It's a little bit earlier, but now it's good time to close the meeting, maybe webinar. Or are there any other information from your side?
Yeah, thank you very much. I think the same. So thank you everybody for having been here. I'm fully aware that it was not possible to sort of discuss the whole process, but I hope you had some insight on what we are working on. And it's really our commitment to write a standard, to write a document, which is as helpful as possible. And I think the main help we can provide from IEC is to harmonize these dozens of standards which are just popping up globally at the moment, so that in future when we do European tests, Japanese tests, Chinese tests, or Australian standard tests, or also American tests, that they are so similar that manufacturers would not to produce 3 different devices for 3 different places, but they could be quite close together with one device to serve all purposes. Also, we see that only just in Europe we have many different requirements in different countries, but most of the differences I would assume they are not based because they have to be differences, but just because different people came up with different solutions. But there would not be any reason for not harmonizing these things. So I hope you liked the webinar and you can also support our future work. Feel free to reach out to us also to see some drafts and give your inputs. And yeah, maybe Yoshioka-san back in Magdeburg, do you still have some closing words for the meeting?
Well, thank you for having your time to attend this webinar. I'm very happy to see a lot of people attending this meeting webinar. Also, thank you for the lot of questions from both sides, to the Burgdorf and the Magdeburg. So this is the second trial. And if possible, we would like to continue such a webinar next year. Also, there are 2 years later. And then I hope that we could develop our testing standard 6349 as soon as possible. Thank you very much for everybody attending this webinar. Thank you. So, Christoph, you can close it.
Thank you very much. I wish you all a very happy Christmas. And in German we say a gute Rutsch ins neue Jahr. So a happy new year once it comes, and not too much stress in the rest of the year if you have to finish your things. All the best and see you on our next webinar. Goodbye. Thank you.
Thank you very much. Goodbye, everybody.